The question reads, how many of these molecules are polar? And the question is followed by a list of molecules including SO3, OF2, BeCl2, CCl4, and O3. To solve this problem, we are going to do three basic things for each molecule. First, we are going to draw the Lewis structure. Secondly, we are going to identify bond dipoles using differences in electronegativity. The third step is to identify net molecular dipoles based on molecular geometries. We will approach this problem by solving each molecule one by one. The first molecule that we are going to solve will be SO3. First, we want to draw the Lewis structure. SO3 has 24 valence electrons. We want to use these electrons to fill up the outer atoms first so that they will have an octet. As you can see here, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons on the outer atoms. So the central atom will not have any electrons. This Lewis structure is valid, but it is not the best Lewis structure. The best Lewis structure would have formal charges as close to zero as possible. In this case, the best Lewis structure involves the central atom having 3 double bonds attached to it. This is okay because sulfur is an octet violator, meaning that it can hold more than 8 electrons. This Lewis structure still has 24 valence electrons, and the formal charges are closer to zero than in this Lewis structure. So this is the best Lewis structure and the one we will use to finish solving the problem. Next, we will determine the bond dipoles. The highest electronegative atom, which is O, will have partial negative charges. This means that the central atom will have a partial positive charge. The bond dipoles will look like this, with the tails facing the central positive atom and the heads facing the more electronegative negative atom. These arrows show you the direction of the charge separation. The length of the arrow represents the magnitude of the charge separation. To determine if the bond dipoles cancel or not, we will have to look at the molecular geometry. This molecule has 3 domains. Which means that it is a trigonal planar electron geometry, domain geometry. The molecular geometry will also be trigonal planar. So the molecule will look like this. So now the bond dipoles will look like this. The rule states that in order for all of the dipoles to cancel, the domains have to be the same. Since all of the domains are the same on the central atom, the dipoles cancel and there is no net molecular dipole. So the molecule is nonpolar. The next molecule we will examine will be OF2. OF2 has 20 valence electrons, and as you can see, this Lewis structure has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 valence electrons. So this Lewis structure is correct, and it is the one we will use. Next, we will determine the bond dipoles. F will have partial negative charges because it is the most electronegative atom. Because of this, O will have a partial positive charge. The bond dipoles will extend from the central atom to the outside atoms. To find the molecular dipoles, we have to determine the domain and molecular geometries. The O atom has 1, 2, 3, 4 domains, so it has a tetrahedral domain geometry. The molecular geometry will be bent because the domains are 2 bonding and 2 non-bonding. This is what the molecular dipoles will look like. All 4 domains are not the same because 2 of them are non-bonding domains. They add together to form a net dipole, so they can't cancel out. As a result, this molecule is polar. The next molecule we're going to look at is BeCl2. BeCl2 has 16 valence electrons, and as you can see, this Lewis structure has 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. You may wonder why the Be only has 4 electrons, but it is because this atom is an octet violator, meaning that it can have less than 8 electrons. Next, we will determine the bond dipoles. Cl will have a partial negative charge because it is the more electronegative atom, and Be will have a partial positive charge. The bond dipoles will extend from the center atom out to the outside atoms. To find molecular dipoles, we must determine the domain and molecular geometries. The Be atom has 2 domains, here and here, both of which are bonding, so the domain and molecular geometries will both be linear. And the dipoles will look like this. Since all of the domains are the same, the bond dipoles will cancel and there will be no net dipole. Because of this, the molecule is nonpolar. Next, we are going to look at CCl4. This molecule has 32 valence electrons, and as you can see, the Lewis structure has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 valence electrons. In determining bond dipoles, a partial negative charge can be placed on the Cl atoms because they are more electronegative. So the partial positive charge would be placed on the central C atom. The bond dipoles extend from the central atom to the outside atoms. Next, we need to determine the molecular dipoles by finding the domain and molecular geometries. The C atom has 4 bonding domains, so both the domain and molecular geometries are tetrahedral, and the molecule will look like this. From here, we will draw the new bond dipoles, which will look like this. Because all 4 of the domains are the same, this bond dipoles will cancel out and there will be no net dipole, which means that this molecule is nonpolar. The last molecule that we will look at will be O3. O3 has 18 valence electrons, and this molecule displays resonance, which means that there are multiple ways to draw the Lewis structure, as you can see here. Both of these structures contain 18 valence electrons, so either one could work. O3 is a more complicated molecule because there are no partial charges, And there are also no bond dipoles. This is due to the fact that the electronegativities of the same atom cancel out. To determine the molecular dipoles, we must determine the domain and molecular geometries. The central O atom has 3 domains, here, here, and here. So it is a trigonal planar geometry. It has 2 bonding domains and 1 non-bonding domains. So the molecular geometry is bent. Since all of the domains are not the same because of this non-bonding pair here, the molecule is polar. Looking back on the original question, we can check off the molecules that are polar, and we find that OF2 and O3 are the only polar molecules in this question. So out of the 5 molecules, 2 are polar. The last thing I want to discuss for this problem is the possible common mistakes that students can make. One of the biggest common mistakes is that people mess up in drawing the basic Lewis structures. This is a problem because a wrong Lewis structure can lead to a wrong molecular geometry, which can in turn affect the polarity of the molecule. Before moving on in the question, make sure that you have the correct Lewis structure.